Okay, VCAA 2021 exam question number 18 for chemistry. And we have these following equations, and then we've got a lot of graphs over 2 pages. So which of these is consistent with what we've got up here? So let's have a look at the first one and let's try and mash that out. This here is the first equation here. I can see the fact that I'm starting off with 2NO2, which is part of this one. It's forming 2NO, so therefore it is this equation. Is this a endothermic reaction? No, that's exothermic, so I'm going to cross that out. The next one is the reverse equation of this one here. So therefore I've got NO2 plus CO, NO2 plus CO, so therefore it's this one, but it's going backwards. This is an endothermic reaction again, which is good. Actually, the reverse reaction should be endothermic, so therefore, because we're going up. So it's not going to be that one. This is exothermic. The Ford's reaction shows exothermic. It's incorrect because it's going back the other way. Let's have a look at the next two. Here we've got dinitrogen tetroxide, so therefore we're dealing with this reaction here. And this one is showing the backwards reaction. So therefore the backwards reaction for this one should be positive 57. So therefore it's going up, which is good. It's going up by 57. That's about 57 there. So that's looking pretty good at the moment. Just to make sure this next one's bogus as well. The next one is the reverse reaction of this. So we're going backwards, but we're also, yep, it's just going backwards. This backwards should be negative 181. So what is the difference here? Is it negative 181? It's close to it. It's looking pretty good. But let's have a look. That's going down here. It's just, I reckon that's just shy of it. Negative 181 was pretty much in the middle there. I'm going with C. Answer C. Let's go with C. So therefore our answer there is C. It's the one that's most consistent with this reaction there. Let's move on to question 19. Question 19, we have a food chemist conducted an experiment in a bomb calorimeter. So we're looking at some calculations here. In joules per gram, this much muesli bar. Okay, we want joules per gram, so we want energy divided by mass, so therefore something divided by 3.95. What is my energy? I've got a calorimetry factor there, so my energy is going to be the CF times by my temperature change, so therefore it's going to be 4780 times by my temperature change of 16.7. Get my calculator, which I've lost for some reason. I'm going to need to find that actually. I don't know where it is. But let's just go with this. Actually, I'm going to have to do it. Okay, calculator. I haven't got it with me. I'm just going to use my computer here. It is going to be 4780 multiplied by 16.7. That gives me 79826. So therefore 79826 divided by 3.9, so divide that by 3.95, gives me 20,209. All right, that's joules per gram, which comes up to being answer of B. Fantastic. Let's move on to question 20 and 21. Question 21, 1 Faraday is equivalent to the mole charge on 1 mole of electrons. Fantastic. The mass of nickel that can be electroplated when we use that many Faradays of charge is what? So if that many Faradays of charge, that means that many, so 200 mole, so 320 mole of electrons. What is the ratio of electrons to nickel? My equation will be Ni2 positive. Ratio to electrons is going to be 2 electrons, so I'm going to have that divided by 2 equals my number of moles of nickel, because every nickel is going to take up 2 electrons. So my number of moles of nickel equals 160. I can then find my mass of my nickel, which is going to be mass of nickel is N times MR. So 160 times by my molar mass of nickel, which I should have on my periodic table here somewhere. Something like 60 from memory, but anyway, let's have a look at it. Nickel is 58.6. 58.7. So therefore, again, whack into my calculator, 160 times by 58.7 gives me approximately 9392. So my answer there is C. Fantastic. Let's move on to using the electrochemical series. Which of the following changes to the electrolytic cell may reduce the amount of nickel plated onto the platinum electrode? Okay, so if I get to my electrochemical series, what I've got here is I've got nickel reacting. So this is my reaction here. If I want that to stop happening, alrighty, I would need to add a something that's more of a stronger oxidant, so something above it here, and that would be oxidized in preference. So let's have a look at what's going on. So replacing that with copper. If I replace the nickel electrode with copper, that shouldn't change too much, I don't think, but let's have a look. It means I'm going to have that, so therefore that's going to be reacting as my anode instead of my nickel, which means I don't have as much nickel in the system in general, but I've got a nickel solution. I've got liquid nickel here anyway, so that shouldn't impact it too much. Replacing nickel liquid with 1 molar aqueous nickel, that shouldn't change the reactions that are going to happen. All right. Replacing the platinum electrode with lead, so therefore my cathode, changing that with lead, that's still going to mean that nickel is my strongest oxidant here. That's not going to happen. So no. Replacing the nickel liquid with nickel chloride. Oh, I can't even see that. Moving on. We're still going to have nickel 2. Again, that's going to simply just going to change. So therefore, that's going to react. That's going to still mean nickel is going to be my strongest reductant. The only thing that's going to change the amount of nickel present in my system is going to be this one here. Because instead of producing nickel, instead of producing nickel ions, because this guy here, he's going to produce nickel ions. Sorry, this guy here, he's going to produce nickel ions. If I change that to copper, it's going to produce copper ions. So therefore, I'm not going to have my nickel replenishing my nickel in my system. So I reckon A is going to be the most correct answer here. I don't like any of these, but A is probably going to be my answer I'm going to roll with there, because it's going to stop the nickel from being replenished when it actually reacts and when the charge is on. So hopefully that makes sense there. Anyway, let's move on to question 22, and then we'll finish off with this video. 1 litre of octane has a mass of that at standard laboratory conditions. The efficiency of a reaction when undergoing combustion is 25%. That's pretty low. What volume of octane stored in a petrol tank can produce that much of usable energy? Alrighty, so what I've got is what is the heat of combustion of octane? So heat of combustion of octane, going to my data booklet. According to my data booklet, heat of combustion of octane is 47.9 kilojoules per gram. So how many grams is going to be there? I've got 528,000 kilojoules. Divide that by 47.9. There's my bell. I'll do that on my calculator here because I haven't got the one that I normally use. But 528,000 divided by 47.9 gives me 11022.96 grams of octane is going to be there. So therefore, how many litres is that? I'll divide that by 703 to get to litres, because I know that 1 litre is this much. So therefore, if I divide that by 703, I'm going to get to 15.68. litres. Now I haven't factored in this 25%, so therefore this is going to be 25% of the actual number that I need to do. So therefore, if I look at this, the answer is going to be D, because I need to get a larger number than that for lack of better calculations there. Basically, I know that this here is 25% of my actual amount of fuel I need to use, because it's 25% efficiency. So whatever number I calculate here is based on 100% efficiency. So therefore, I need to factor that up to whatever it would have been with that efficiency taken into account. Anyway, that's question 22. I'm done here. I need to go home and I'll continue this later on.